Welcome back to the videotape review and solution. This is the third part of the regression review, which focuses on the inference for future response and the inference for future observations, which is also called prediction interval. Let us recapitulate for the linear model. We have our simple linear model yi equals to the beta 0 plus beta 1 xi plus epsilon I for observations I equals to 1, 2, up to n. Now, we have the distribution of y, which is our response given xi, follows the normal distribution with beta 0 plus beta 1 xi as the mean, and and sigma square for the variance. For a new observations x star, we therefore have the distribution of y given x star follows a normal distribution with mean beta 0 plus beta 1 times the new value x star with the variance sigma square. So right now, let me put the y hat, which is our predicted value over the regression, doing the regression from R or from JMP, the y hat equals to the beta 0 hat plus the beta 1 hat times the x star when we know that the new observation x star. So our expected value for the y hat is exactly the beta 0 plus the beta 1 x star, whereas our variance of y star is the sigma square times 1 over n plus x star minus x bar, which is the mean of x to the square over the corrected ss, which is the summation of I equals to 1 to n xi minus x bar to the square. Notice that the sigma square here denotes the MSE, which is also the square of RMSE. To know about the detail of the derivation, you can go to my class note 22 and 23. I omit the detail here for the sake of the exam. Now, for the estimated standard deviation for the y hat, we have s to the y hat equals to the s times the square of 1 over n plus x star minus x bar squared over the corrected ss, which is the summation of I equals to 1n xi minus x bar to the square, where here the s denotes the RMSE equals the square root of MSE, which is also the square root of the summation of I equals to 1 to n for the yi minus the yi hat square over n minus 2, which also equals to the square of 1 minus the correlation r to the square times the summation of I equals to 1 to n yi minus y bar, which is the mean response, to the square over n minus 2. Now, for the hypothesis testing, therefore, we are using the test statistic for the y hat defined above minus the beta 0 plus beta 1 x star over s to the y hat follows t distribution of n minus 2. So in detail, we have the h naught, which is the null hypothesis, is beta 0 plus beta 1 x star equal a particular value mu 0 versus our alternative hypothesis h1 is beta 0 plus beta 1 x star not equals to that particular value mu 0. Remember, we have the degree of freedom n minus 2 because we are estimating the intercept beta 0 and the slope beta 1. And we do the same step as we had taught before in the part 2 for the hypothesis testing for the slope and the intercept. We are deriving the t statistics and find out the p-value and compare the p-value to the significance level and to decide whether we reject the null hypothesis or not and make the conclusion. Significantly, we also focus on the confidence interval for mean response because I believe this is more often to be tested during the exam. To construct the percentage of confidence interval for mean response, we use our observed value beta 0 hat plus beta 1 hat x star. This is the value for the y hat plus or minus the t to the n minus 2 degree of freedom with the level alpha over 2 times the s of y hat defined above. This is our confidence interval, which is also the beta naught hat plus beta 1 hat x star plus or minus the t to the degree of freedom n minus 2 with level alpha over 2 times the square root of the MSE times bracket 1 over n plus x star minus x bar, which is the mean response. X star is a given value in the question, to the square over the corrected SS, which is the corrected sum of square, equals to the summation of I equals to 1 to n xi minus x bar square. For the confidence lower bound or confidence upper bound, we will either do the beta 0 hat plus beta 1 hat x star plus the t to the n minus 2 to the level alpha times the sy hat, or the beta 0 hat plus beta 1 hat x star minus t to the n minus 2 degree of freedom with level alpha times s to the y hat. This is about the inference for mean response. For the inference for future observations, which is the prediction interval, we first notice that the error in prediction is calculated by the observed for y minus the y hat, which is beta 0 plus beta 1 x star plus the epsilon for the particular observation minus the predicted value beta 0 hat plus the beta 1 hat x star. Since the future observations is also assumed to be independent from the normal assumption we have defined, we need the observations are independent for linear model. We have the new value y new equals to beta 0 plus beta 1 x star plus the epsilon to be independent of the observed values before. We should have the covariance of the y new and the y hat equals to 0. Therefore, we have a nice formula for the error of prediction of the variance, particularly the variance of the y new minus the y hat equal to the sigma squared times 1 plus 1 over n plus our new value x star minus the mean value x bar to the square over the corrected SS, which is the summation of I equals to 1 to n xi minus x bar to the square. This value could be derived from a lot of steps in our class notes. Particularly, the sigma square is the MSE. to perform our hypothesis, we also do the estimated standard deviation of y new, which is the s to the y new equals to the s to the y hat square plus s squared, taking square root of them, which equals to the s times 1 plus 1 over n plus the x star minus x bar squared over the summation of I equals to 1 to n xi minus x bar squared, taking square root of them, which is the RMSE times the square root of 1 plus 1 over n plus the new value x star minus the mean value x bar to the square over sum of square. Therefore, for hypothesis testing, we have our null hypothesis, which is the beta 0 plus beta 1 x star. That value equals to a particular value mu 0, whereas the alternative hypothesis is the beta 0 plus beta 1 x star not equals to that particular value. And our t statistics should be the y new, the new observed number, minus the thing that we put into our null hypothesis over the s to the y new follows the t distribution with n minus 2 degree of freedom. Remember, we are also having degree of freedom n minus 2 because we estimated the intercept beta 0 and the slope beta 1. We also compare to the t-table and find out the p-value, and then derive our conclusion. To construct the percentage prediction interval for future observations, we typically have the beta 0 hat plus beta 1 hat x star plus or minus the t to the n minus 2 degree of freedom and alpha over 2 level times the s to the y new, which is equals to the beta 0 hat plus beta 1 hat x star plus or minus the t to the n minus 2 degree of freedom and alpha over 2 times the MSE equals to MSE times 1 plus 1 over n plus the new value x star minus the mean value x bar square over the sum of square, taking the square root of them. For the confidence lower bound, for the confidence upper bound, we have the same. When we also have the same, approximately some percent confident that our prediction interval falls between the value that we have derived above. Thank you very much for the attention.